Hey there, welcome back to 2241. Today we're going to talk about the dot product of vectors. And so as you can see, we have our terms, formulas, and objectives all laid out here as usual. And let's see what the first section, the terms, says. So the dot product is a way of multiplying vectors. And in order to understand that, we are going to go through these terms. So what the dot product is, it's also sometimes called the scalar or inner product for various reasons that I'll explain when we get to the terms. We are going to look at the angle between vectors and what that means. We're going to look at orthogonality, direction angles and cosines, vector and scalar projections of vectors, and then last, a physical thing, work. All right, so we'll talk about those on the next page, and right now we're going to move on to the formulae. So we have, as usual, our two vectors u and v with components 1, 2, 3, 1, 2, 3. And here is the mathematical definition of the dot product. So we have two versions of it. This one usually comes first, actually, and so I'll say that one first. U dot v is equal to the sum of each component multiplied together. So it's sort of like the norm, but doesn't have a square root, and you multiply corresponding components of these vectors instead of just multiplying these guys by themselves. All right, and then we have the geometric definition. And you can actually show that this definition implies this definition, and I might do that in an explanation video for this section. But the geometric definition says, all right, well, instead of doing this component-wise thing, I can just look at the lengths of the vectors, multiply them together, and then multiply by the cosine of the angle between them. And this also has sort of a derivation that I'll show you in the video, or maybe an intuitive explanation is a better way to describe that. I'll put that in the explanations video. All right, so then there's this cosine theta thing, and what is that? Where does that come from? Well, it is the angle between the two vectors u and v. And so it's defined by this formula, and that's what we use to calculate it whenever we need to. Notice it says the cosine, but I'm defining the angle. It's just a little bit easier to write it this way and easier to sometimes think of the cosine. You don't always actually need the theta by itself. So this is usually a nicer way to write the formula. All right, orthogonality. So we have u is orthogonal, that's what this symbol means, to v, if and only if u dot v is equal to 0. So it is possible for two non-zero vectors to multiply to 0. And if that happens, they're called orthogonal. Orthogonality is kind of like perpendicularity. And again, we'll see that when we get to the next page. All right, so direction cosines. What are these guys? These are the cosines of the angles that a vector u makes with the x, y, and z axes. In particular, they are what you get if you take v here and replace it with I, j, and k, the standard basis vectors. So you've got these formulas where you take the components and divide them by the norms. So this is also just the components of the unit vector in the direction u. All right, almost done here. The projection of a vector onto another vector, so v onto u. The notation here is a little bit weird, but just bear with it. You'll have to try and get used to that. The scalar projection is written this way. It's comp for component, the component of v in the direction of u. And this is the dot product of u and v divided by the norm. of u. And then the vector projection is the projection of v onto u given by u dot v divided by norm of u squared times the vector u. Or, maybe written a little bit more clearly, it is u dot v divided by norm u times u hat, the unit vector in the same direction as u. But this part right here is just the component of v in the unit vector direction, or in the direction of u. Notice that this number right here is a scalar. It is a number and not a vector. So the dot product right here will give us back a number, while the vector projection should give us back a vector. And it does because the component here is a number and we multiply it onto a unit vector. So it takes this unit vector and scales it by the appropriate amount to give us the projection of v. All right, last is work. And again, this is a physics thing, but it can be written mathematically. So work is the capacity or the amount of energy it takes to move an object by a certain amount. Energy is the capacity of an object to do work. But they're sort of interchangeable. And so the way that we compute work is we say, all right, well, I pick something up and I exert a force to move it. So I exert some force in some direction using a vector. And I say, all right, how much did I do? And in what direction? The cosine accounts for how much of this force is actually doing the moving. And then this here, vector d, is the displacement vector. So this is how the object actually moves. There might be other forces acting on it. Like if I throw a wiffle ball into a really strong windstorm, I will have done a little bit of work on the ball, but the windstorm will do a lot more work because the ball will go out and then fly way back past me. But that is the definition of work. It is the sort of how much the force that you're looking at gets what it wants. And if we rewrite this a little bit, earlier, but we'll do it now. You have the norm of f times the norm of d times the cosine of the angle between them, theta. And this, according to our geometric definition above, is just the dot product of the force and the displacement. All right, so that is the definition of work, and that is all of our formulae. So next we're going to go over our objectives. And we have easy, medium, and hard as usual. I tried to make these a little bit shorter and I kind of failed, but they are not too bad, I think. So the easy ones, remember both dot product formulas. I think that's pretty straightforward. Remember what kind of object u dot v gives. And my question here to you is it a scalar or is it a vector? Does it give you a number or a thing that has a direction as well? Next is know what orthogonal vectors are and how to check for orthogonality. So if you're given two different vectors, can you tell me whether they are orthogonal or not? That formula we just saw is a test for whether two vectors are orthogonal. All right, next up is the medium objectives. First one says, do vector algebra comfortably with the dot product. So in the last section, you learned how to do vector algebra using like vector addition and scalar multiplication. Now, can you still do it when equations or expressions involve the dot product as well? All right, next we have computing angles between vectors and direction cosines easily. There's another formula for that, we just went over it. Basically, I'm just saying I want you to be able to remember and use that formula and know when you need to do so. Next one is use the dot product to find work done by a given force. Use this formula. So a lot of this is just, can you use these formulas comfortably without getting confused? And last is compute scalar and vector projections. Okay, cool. So all of the medium stuff, I just want you to be able to compute things. Now for the hard ones. And remember, these are not objectives that you need to have by the end of today. So I want you to eventually understand what the dot product measures geometrically. That's something that'll show up in the explanation video. I also want you to recognize when the dot product applies to physical problems. This is part of learning how to translate word problems into mathematical problems and not just get totally confused by word problems that might pop up. Okay, and then we have, last but not least, use the dot product to derive the Cauchy-Schwarz and triangle inequalities. I've put these in the homework as challenge problems. So these are more difficult than the hard problems. They involve proof, but if you are going to go into a mathematics heavy career or something that involves proof, this is a very good exercise for you. If you are not, then feel free to completely ignore these. You do not have to worry about that objective at all. All right, and here is the terms page. So let's go through these one at a time. And then after that, we will end the video and go to the examples video. So first off is our dot product. So this is called the dot product, well, because it uses a dot as a symbol. It's also sometimes called the scalar product, because what happens when I do the dot product, and I use two vectors here to compute this, well, what I get out is just a number. Remember from that formula, the algebraic one, that it is u1 v1 plus u2 v2 plus u3 v3. And all of these things are just real numbers. They're the components of the vector along the x, y, and z axes. And we multiply real numbers and add them all together, and that gives us back a real number. So what comes out of the dot product is not another vector, but a real number. The same thing here. Now, on this right here, this copy of the real line that's telling you, okay, this thing comes out as a number, notice that I've drawn the dot product of u and v coming out as a positive number, and the dot product of v and w as a negative number. That is also possible. Basically, what the positive or negative tells you is whether the vectors are pointing in this more or less in the same direction. What I mean by that is, all right, if I sort of look at the line perpendicular to v right here, well, u is on the same side of the line as v, whereas w is not. So if I look at that perpendicular line at the initial point of v, w points in the opposite direction, points to the negative side of that line, while v points in the positive side. So that's what the positive or negative means here. Now, last, this is called the inner product for some slightly different reasons. I guess we don't really need to worry too much about that. So it is sometimes called the inner product. You will probably hear me call it the inner product once or twice. If I do, just think dot or scalar product. Cool thing is that it also has some algebraic properties, and it would be nice to know those so that we can actually do the algebra with them. So first off, we have that if you take the dot product of a vector with itself, you get its length squared. And That also means that if you take the dot product of a vector with itself, and then you take the square root of the number you get out, that is another way of computing the norm. Well, it's not really another way. It's just if you expand this formula out, you get square root of u1 times u1 plus u2 times u2 plus u3 times u3. And so you get, well, exactly the norm formula again. It just looks a little bit different. What this really gives us is a way of computing the dot product of a vector with itself from the norm. Okay, and the second property here is we have that the dot product is commutative, so you're allowed to swap things around. You don't have to worry about this being like matrices. Third, you can distribute the dot product over vector addition. Note that the dot product has to be between two vectors, and so these things in here also have to both be vectors. If this was a real number and that was a vector, this wouldn't make sense, because I would end up with u dot a vector plus u dot, what I've just written without arrow, a real number, and that would be nonsense. 4 is this kind of cool property. It looks just like association, but you want to be very careful again about what these objects are. So u and v are vectors, and r is a real number. So they're different types of things, and we need to make sure that we know what's going on here. So what this side is saying is if you scale a vector and then dot product it with another vector, that's the same as dot producting both of the vectors first and then scaling the result, or scaling the other vector by the exact same amount and then doing the dot product. So all three of these things are the same. And last is if you take the dot product of a vector with the zero vector here, it's got that little arrow up there, what you get out is the number 0. Note this is not a vector anymore. Again, the dot product gives you back a scalar when you put in two vectors. So dot product with the 0 vector gives you the 0 number, the 0 scalar. Okay, and so those are our properties of the dot product that work algebraically. Next is the angle between vectors. So this is another way of measuring, right, whether the dot product is going to be positive or negative. And you look at that cosine right there. So here is our formula for the cosine of the angle between them. And this will pop up again in the explanation video. So this is just a way of computing that angle right there, given any two vectors. And because these things are, we can compute them algebraically, just use this formula and then the norm formula. You don't actually have to look at these vectors at all or think too hard about any sort of trigonometry in order to do this. So you're getting a trig value by not doing any trig, or maybe not even remembering any values on the unit circle to get this. It's very, very convenient when you just need the number and you don't want to have to go through all of that remembering your angles stuff. All right, next is orthogonality. So in 2 dimensions, 3 dimensions, finitely many dimensions, orthogonal is just another word for perpendicular. In general, it's kind of a generalized version of perpendicularity because you can do it in infinite dimensions as well. But orthogonality, for now, you can just think of as u and v point at right angles to each other. And that's what this symbol right here means. U and v are orthogonal, perpendicular. And here's a picture of what that looks like. Now, why does the dot product being 0 mean that they're orthogonal? Well, if I move this over a little bit and we do this example right here, you know that I and j are orthogonal vectors, or hopefully you do. And let me change that, that's fine. So here's my vector I, and here's my vector j, and I want to take their dot product. Okay, well, I looks like this, 1, 0, 0, and j looks like this, 0, 1, 0. Well, I did that. Okay, I drew them in 2 dimensions here, but they also exist in 3 dimensions. And so if I do the dot product, I get 1 times 0 plus 0 times 1 plus 0 times 0, and that's 0. Okay, I could also do this with other vectors. Let's say something like, what's a good one here? How about, I think this will work. Let's do 1, 1, 1, dot 1, negative 1, 0. I believe that'll work. Okay, so in that last dot product example that we did, we got all of the terms equal to 0, and so that's why everything canceled out and we got 0. But the terms themselves do not have to end up being 0. Now here we get 1 times 1 plus 1 times negative 1 plus 1 times 0. And that gives us 1 minus 1 equals 0. So the terms can end up just canceling out in the algebra. Another thing is that this is not the only vector that has dot product 0 with 1, 1, 1. What if I do something like negative 1, negative 1, and then let's see, I think I need a 2 there. That should work. Let's see what happens if I try to do that one. Let's move this up a little bit. So what about this dot product now? Well, I get 1 times negative 1 plus 1 times negative 1 plus 1 times 2. That gives me negative 1 minus 1 plus 2. Well, yep, that is 0. So I started with the same vector on the left side in both examples and different vectors on the right side in both examples. And these both ended up giving me a dot product of 0. And that is because there are many different ways to point at right angles with the vector v. So, or with the vector u, I'm sorry. All of these vectors right here that I'm drawing little right angle squares at are at right angles with u. They're all in the same plane, and they give me a dot product of 0 with u. And I think I've chosen these nicely enough that I can do this next part as well. Let's see, 1 minus 1, 1 minus 1, 0, and then dot minus 1, minus 1, 2. And I believe that these should end up giving me 0 as well. So 1 times minus 1 plus minus 1 times minus 1 plus 0 times 2. And I think that's going to work out. Negative 1 plus 1 equals 0. So all of these vectors are at right angles to each other. If you are going to take linear algebra, this actually helps you see that these vectors, 1, 1, 1, 1 minus 1, 0, and minus 1, minus 1, 2, those vectors form what's called a basis for XYZ space. So we have these standard basis vectors, I, J, and K, but then you can also try to write all of the vectors in XYZ space as scaled versions of these 3 vectors. And that gives you what's called a basis. All right, so next is the direction, angles, and cosines. This is just finding the angle between a given vector and some very specific vectors, your basis vectors, I, J, and K. And so the direction angles for this basis are usually called alpha, beta, and gamma. the Greek letters. And I've done some shorthand notation here, but basically this is just meant to be cosine of alpha equals the first coordinate of u divided by its norm. Cosine of beta is the second coordinate of u divided by its norm. Cosine of gamma is the third coordinate of u divided by its norm. And what's happening here, if you think of this thing as the whole vector u, this is the formula for the unit vector in the direction of u. And so all of these components should be on the unit sphere in 3 dimensions. Draw that here. Here we go. And with my XYZ axes, this guy should be size 1, 1, 1, 1 here. And all of those vectors, the scaled components by the norm, should end up right somewhere here on the sphere. And so it kind of makes sense if you're thinking of like the unit circle. Now we've got the unit sphere. You just take the component, scale it back to the unit, and then you should get out the cosine of the angle with that axis. Maybe that doesn't make sense, but hopefully it does, at least a little bit. All right, so now let's talk about the vector and scalar projections. So the idea behind projection is exactly what it sounds like. You project. You can think of maybe putting a light bulb way out at infinity here, and then the light shining down onto these vectors and at right angles. And so right here, what you see as the shadow of this vector v on the vector u, that the length of that shadow is the component of v in the direction of the vector u. So if you were to use u as a basis, maybe or u as a basis vector, then the component of v in the direction of u would literally be one of the coordinates of v if you were to write it using that basis. The projection, the vector projection here of the vector v onto u is that same thing. I just moved it over here and then put an arrow on it. And that's what that formula reflects. You take the unit vector u hat and you multiply it by the component of v in that correct direction here. And so it's basically just, all right, measure the shadow, and then do you want to put an arrow on it or not? All right, last here for this video is the work in a physical sense. So you've got this big box here. It's very heavy, and you're pulling it by a rope attached down here. And so when you're pulling it, you're exerting a force sort of in that direction, but also in that direction because it's attached below where you're pulling it from. If you were crouched way down and you pulled it directly in this direction, your force would go horizontally. But this is meant to illustrate the dot product, so I have it up in this direction. Okay, but when I pull that box, well, gravity's pushing it down, so it's going to stay on the floor while I pull it, and it's going to be displaced in this direction, horizontally. So I'm pulling with some force, but not all of my force is going into pulling the box that direction, only the horizontal component, the projection of F onto that vector is what's pulling the box. And thus, the work here is just sort of a measure of how much that force that you're exerting is getting what it wants. All right, its goal is to move this box in the same direction. It's getting some of that, because this displacement is also sort of in the same direction as F, but not quite. There's a non-zero angle between the two. Okay, and that is it for the terms, and in the next video, we will cover examples.